And the homework is also assigned. Let's go over some examples of how do we apply, how do we see what is the problem statement, and looking at the VDS, we make decision if it's in the triode region or is it in the saturation region, because that would then help us apply the right equation to solve and to find out parameters. We'll also look at the examples of how do we use transistor in a circuit and how do we calculate that. All right, so let's wait for a couple of more minutes to people to join in. So this is, I think this is exercise 5.1. Now we have seen the parameters, oxide thickness, mobility, the transconductance parameter, length, effect. So we have to identify what is the question thing and apply the right situation to that. So here we are asked to find the required value of W, the width. And this is something which goes back to the relationship of the conductance or the resistance. So let's see how do we deal with this. So the first thing is we have to find we are given the fabrication process, thickness of oxide, mobility, and we have to find the process transconductance parameter. So if we remember, that's mu n and oxide capacitance. So here we are given this thing, we are not given this thing, but we have been given the oxide thickness. So we can find out what is the capacitance by the relationship of E ox divided by T ox. So this is, we know for silicon, the value for this, which is 34.5 picofarad per meter divided by, we are given the oxide thickness. So we just plug in the value, which is 4 nanometer. We can find out oxide thickness. So here I've done the calculation already. It's 8.625 femtofarads per micrometer squared. So we know this guy, we find this guy. So we just plug in the value and we get 388 microamp per volt square. All right, so now we want to find out the width. If you remember, the width is related to drain current, and it's also related to the conductance between source and drain, which is 1 over RDS. So what we have to do is we have to find RDS, which is Ohm's law. But what is the voltage? So in Ohm's law, we have V equals IR, right? So here R is equal to V over I. So we are given both resistance and voltage here, but we have to find the width. How do we relate this with the width? We, from this guy here, it will be overdrive voltage. I'm just putting it in just to show that this is how we'll get, divided by the drain current, right? So we are finding the transistor resistance. So we have to find both of these things to get there. So
Professor.
Yeah.
Oh, sorry to interrupt. Where'd you get the 3.5 on the first screen, that
Okay, this
34.5.
we discussed that. So this is a parameter which we know, permittivity
Okay.
for oxide. When at the start we went through this way to, so oxide, there's a constant, there's a
Okay.
no for oxide permittivity.
Okay, just want to make sure. Thank you.
All right. So here we need these two things, and overdrive voltage, we know this is fundamental relationship. We use it in different variations. The overdrive voltage is the gate to source voltage minus the threshold voltage. So that's the voltage we have to crank up above the threshold voltage, right? So this is now given, we have the VT here, and we are given the VGS. So we plug in, and what we get is 1 minus 0.5, which is 0.5 volts. Now, ID, what is the drain current? So that's, we know Kn prime W over L. We know that basic fundamental relationship for the drain current. So we plug in the value, we just found this. What we are missing is this guy, because the length is given here. .18 micrometer fabrication process. So channel length is a fundamental parameter which defines how do we do this. So we plug in the values. This goes as is in this relationship, and this goes as in this relationship. So we can write down GDS is equal to Kn prime W over L POV divided by 1. So we play with this, and this comes up, and VOV is half. So that sorry, so there was half here, which gets taken care. And this is equal to, so we are given 1 volt, and we are given the RDS 1 kilo ohm. So this is equal to 1 over 1 kilo ohm. So plugging in all those values, we get W over L equals a ratio of these two guys, 5.15. We know this guy, 0.18. So that gives us the width of the device, which is 0.93 micrometers. Right, so looking at the problem statement, we have to see what is the situation, how is it operating, and how do we plug in the values. All right, any questions on this? Now this one is talking about 65 nanometer process, which means L is 65 nanometer. Again, we are given oxide thickness, mobility, threshold voltage, and we have to find Cox and Kn prime. Just like the last question, we'll find those values, right? So I'm just gonna write, so Cox, again, epsilon oxide is known, it's a constant, oxide thickness is given, and we get 24.6 femtofarad per micrometer squared. And Kn prime is then mobility times, and this is N MOSFET we are talking so far, right? So we have a value for Kn prime also, it's 531 microamp per volt squared. All right. So we are given the ratio of W over L. We are given saturation. We're given drain current. Now, in saturation, we have to remember what is the situation for saturation. Saturation is when the drain voltage exceeds gate voltage, when this guy exceeds this guy, right? So we get into saturation. So we have to apply the saturation relationship for drain current, which is half Kn prime W over L overdrive voltage squared. So we don't know this guy, but we know everything else. We are given the drain current. We found out this guy. We are given the ratio of these two. So we are going to put the drain. We're going to find the overdrive voltage from this. So VOV squared, you'll get some value. So that gives us VOV to be 0.14 volt. Now, we have to go back to the fundamental relationship. The gate voltage has to be more than the threshold voltage. So VOV, what we wrote before, where we wrote VOV equals VGS minus VT. So same thing, but now we are given the threshold voltage here, and we have just found out the overdrive voltage. So that gets 0.49 volt. Now for the saturation region, VDS has to be greater than the VOV at a minimum, right? So we get into saturation region. So VDS, minimum value for VDS in this situation is then nothing but VOV. So minimum value of VDS needed to operate it in saturation with these given condition is this, right? So we play with those basic situations depending on which relationship we have to use for that particular situation. All right. So far, so good.
Wait, I have a question.
Yeah, go ahead.
How did you get the COX on top? That was like the first one you calculated.
Yeah, so when we were talking 3 lectures ago, this is the most fundamental relationship for capacitor, for any parallel plate capacitor.
So it's like a constant or like a given?
T oxide is given. This guy is a constant. Epsilon for oxide is a constant.
What's the constant value?
It's 34.5 picofarad per meter. So
34.5?
okay, let me write it down. So epsilon for oxide is a constant, and we discussed this when we started on this. So it's 34.5 picofarad per meter. And that gives you COX from epsilon ox divided by oxide thickness. All right. The oxide thickness is given in the question. So when you read the question, you have to see process technology means the length of channel, and oxide thickness is given, mobility is given. In this case, threshold voltage is given. We find this guy, from this we can find this guy because mobility times oxide capacitance, right? So if you remember, we model oxide as a parallel plate capacitor in which on one side we have the gate and on the other side we have the channel. And this is an insulator, oxide. So we said we can model it like a parallel plate capacitor, and these are fundamental relationships for parallel plate capacitor. Another relationship for parallel plate capacitor is Q equals CV. Charge, if you want to find charge of a capacitor, capacitance times the voltage. Right? So they are covered. We discussed this in first or second lecture of chapter 5.
And you said that the process technology is the length.
Process technology is always the length of the channel.
And does the
So
width have like another name too?
say it again.
The width, would it say like the width, like if it
We
would give it?
we are given the channel width,
Oh, okay.
right? So device is a 3D thing. So you know the length, you need to know the width. So if you know those things, we can find out the current, drain current, right? So if you think about it, the channel is a resistance. So you have source, you have drain. So channel is, if I look at in 3D, I'm just looking at it from a side. This channel is nothing but a resistance through which drain current is flowing. How we create channel is because of gate. And then we have discussed, okay, your drain current is, if you crank up your drain to source voltage above your gate voltage, we get into saturation. And then we can find out how much is the resistance of this, which we just did in the previous question. So this is how we would find the channel resistance between drain and source. So this is all in the lectures that I posted. All right. All right,
Sure.
let's look at another question.
I was curious on how you got 0.14 on
Okay,
on
for
VOV
saturation,
equals.
right. For
But
saturation,
how did you
Right.
get to that point? Could you like show like the actual steps?
this
to it?
one,
Yes.
all right. So we have this relationship for drain current. We know drain current here. We know Kn prime here. We know width and length ratio. The only thing we don't know is this guy, right? So you take everything on the other side. So you have this relationship, something with VOV squared, and everything is on the other side. So you get some number, and then you take its square root, and you get the value for the overdrive voltage. Does it make sense? So why are we using this? Because we are in saturation. Nestor, I cannot hear you. Yeah, if you want to type in chat, let me open the chat. Where did you get 34 point? Okay, that's the epsilon. All right, Nestor, I couldn't quite hear what you just said. The 10-inch, do we need to convert 10-inch to meters? No, we convert everything to micrometers. 10-inch, where is 10-inch? No, this is not inch. This is in saturation. We are given a ratio. We are given ratio of two lengths. Two lengths has no dimension. Length divided by length is no dimension. That in is the ratio in saturation with ID. Got it? This is not inch here. This is just saying that this ratio of that transistor is in saturation. right? W65 nanometer. So yeah, so width to length ratio is given. Okay, 65 nanometer tells you, so there is appendix. If you look at the end of the book, there is appendix K, which gives you mobility for different process technology. So this guy is telling you this. So here it is given to you. But if it's not given, you look at appendix K, you can find out what is the mobility for this process technology, 65 nanometer or 0.18 micrometer. But here the ratio of this thing is given straight away. But yeah, you can find out widths from this as well. Right? So here we didn't need to, but if it was like previous question, yeah, that would have been straightforward answer to find the widths. All right. Let's look at another exercise. So I posted lecture yesterday about early voltage. So early voltage is early was the name of the person of scientist. So the early voltage concept is that in reality, it is not saturation like this. There is still some increase because for this to be valid, that would require infinite resistance, which would mean that if there is slight change, say from here to here in VDS, there would not be any change in drain current, right? So, but that's not true. There is some change. So which means that curve is not exactly a flat line, but curve is slightly going up. So, but then they extended this and we find, and this is happening because of length dependence. So they extended, and this is what we call early voltage, which has the length dependence embedded in this. And this is, its dependence on a parameter we call lambda. It's also dependent on length of the channel. So there is combination of this guy with the length. But we take this VA prime times length, and that's what this guy is, this early voltage. So there's a relationship for that also, which is discussed in lecture yesterday or day for yesterday. So is the question, channel length is given, width is given, they say find VA and lambda. So VA is straight away VA prime times length. So it is, here it is given 5 volt per micrometer times the length is given 0.8 micrometer. So that's your early voltage. Again, you have to understand early voltage has component of length dependence in it because the saturation is not a constant. There is slight change with slight drain voltage even after saturation, right? So that's where it comes from. So we are incorporating length dependence in this situation. And lambda is the length parameter. This is 1 over VA. So we have VA, which is 4 volt here. So we say 1 over 4, we get 0.25 per volt. So its unit of lambda is 1 over volt. All right, so what's the question continues? Find the value of drain current when the device is operated with an OV of this and drain to source voltage of this. Now, let me ask you something. VDS is 0.8, overdrive voltage is 0.2. What kind of operation is this? Is it triode or saturation? Let me clean it a little bit. So our overdrive voltage is 0.2 volts and VDS is 0.8 volt. What is the area of operation for this transistor? This is triode region and this is saturation region. Rule of thumb, you have to go through the previous lectures, but the rule of thumb is if VDS is greater than overdrive voltage, we are in saturation, which means we are pushing VDS is larger than overdrive voltage, and that takes it into saturation region. Are you with me? We have to go through these lectures. Monday's exam, so this is part of that. If you are not comfortable knowing what is the saturation region, what is the triode region, you will not be able to pass the exam. I can tell you right away. So we have to go through the chapter, we have to go through the lecture. So we need to know what is the operation of transistor so you can apply the right equations for that situation. You're with me on this? At least I cannot see you. Evaristo, your video is off.
Yes, sir. Sorry, I'm on cellular data. So if I put the video on, it lags everything.
All right, no problem. Once or twice, that's okay. Don't worry. All right, so I want to hear back. So you guys understand how we define which area of operation the transistor is in? Please repeat back. If this is the situation, what kind of transistor operation is happening?
If VDS is greater than VOV, then we're in saturation. If it's
In
less
saturation. Right.
if it's not, then it would be just irregular.
That would be called, that's called triode operation, right? And for the situation we have different equations that we have to use to find the drain current, right? So it's as simple as that. So you have to identify what is the operation region. You have to remember this by heart. If VDS is larger than overdrive voltage, we are in saturation. All right. So for saturation, drain current is same old formula. But now we have dependence on length. So dependence on length brings in one more factor, and this is covered in yesterday or day for yesterday's lecture. Then we have 1 over lambda VDS. So this lambda brings in the length dependence into the drain current equation. This is what takes care of this length dependence in this situation.
So that one's for saturation.
Sir, you're muted, sir.
Sorry, I sneezed, so I just muted myself. All right. So one thing we see, okay, this tells us is saturation. All right, done. Now the second thing is we are given length dependence here. When we are given VA prime and we are finding the early voltage, that tells us, or the lambda introduction, that tells us there is length dependence here. So when length dependence is there, we have to use this relationship. And this relationship incorporates length dependence through this factor lambda, right? So we know lambda, we just found out. So we plug in the values. We know this guy, we know this guy, we know this guy, we know this guy, and of course we know this guy, right? So we plug in the values, we get the drain current from these 0.192 milliamps. So you have to be careful with units, and there is one homework question which makes you do exactly that exercise of dealing with units when you're doing this. Now we got the drain current, and we have to actually find the output resistance, which just Ohm's law, right? But Ohm's law with drain current and early voltage. So for the output resistance, the relationship is VA over ID. We have just calculated both of these. This is ID. Early voltage we calculated at the start. Hold on, what's going on? It's cranking up everywhere.
Sir,
So I keep the email on just in case somebody is stuck outside or anything. All right, yeah, question.
could you write it all like the KN, the W over L, the VOV, just so we can visualize what you're doing?
All right, so these are in the video lectures, these are all covered. So, and that's, we have went over this. Kn prime is C ox mu
No,
n.
like I know what that is, but I just like want to see what like the actual values are for you to get the answer.
Oh, for in this question?
Yes.
Okay, yeah, yeah. So let me take a step back here. So Kn prime, to find, this is Kn prime, mu and C ox, right? This is Kn prime, right? W over L, length and width is given, W over L, right? VOV is given 0.2 volt. Lambda is VA is 1 over lambda. We just calculated lambda here, right? VDS is given. You with me on this? So all these things are given. So we plug in those, we get the drain current, 0.192 milliamp, right? So now we want to find the output resistance, which we said if it was in saturation, if it was straight line, that would have been infinite, but it is finite, and that comes because of channel length modulation. So we use early voltage, just Ohm's law over drain current. So early voltage we have calculated above, drain current we have calculated here. So that gives me 4 over 0.1 192, somewhere around 25 kilo. Now this ID that's used here is with the channel dependence, right? So now there's question here. If VDS is increased by 1 volt, what is the corresponding change in ID? That's where we have to just use their relative change values. So R naught is equal to delta VDS. the change that's being asked divided by the change in drain current. So this is what we need to find. We know this value, we are given this, so we can find out how much drain current would change by this difference in the source to drain voltage. So let me just raise and put it here. So what we are doing is we are finding how the drain current would change if there is change in the VDS. So 1 volt VDS change divided by the resistance that we found out. So we can find out it's 40 microamps change with this change in drain to source voltage. All right. You'll probably have to go back to go through how we got there. All right, questions. So you'll see we are playing around triode saturation, those few set of equations that we need to know how we apply, where we apply. And we just plug and play it there. I know it seems simpler than it actually is, but you have to practice. You have to do these things to nail down what are we taking and how we are putting in there. So in this question, we are given threshold voltage. So this N is nothing but for N MOSFET, because we'll talk about P Mosfets very soon. In that case, we will write the threshold as VTP, just to identify we are talking about P Mosfets or N MOSFETs. All right, so now we are given this guy, which simplifies my ID. I don't have to find out everything. Now in this case, we are given saturation region, makes my life easy. So I know what ID relationship to use. So the question is, what is the required VGS and the minimum required VDS? So this, we know overdrive voltage relationship. So we'll just plug it into there and we'll repeat for different ID and see how does the gate to source voltage and drain to source voltage change. All right, can somebody help me? What should be the ID equation here? You can look up the book and find the saturation region ID equation. All right. Who's ready to dictate me? I can probably give you a hint where to look for that equation. So here, there's no channel length modulation given or no lambda given or no early voltage given. So we are going to use the simplified relationship. Now, if you guys go to page 263, table 5.1, it tells us in saturation, what is the drain voltage? Oh, sorry, what is the drain current? Can you guys, do you guys see table 5.1 on page 263?
I think it's 1/2 of K naught.
All right,
N.
all right. Alicia, help me
Oh.
write down. So half
Yes, sir. K naught.
Kn prime
Yes, sir. And
and
then in parentheses,
W
W
over
over
L
L. Yes, sir.
and times
VOV squared.
VOV squared. Very good. So straightforward. We are given drain current 50 micron. We are given this factor together here. I'll just plug in. What I don't have is VOV. Now, how is this related to VGS? Okay, this we have to remember by heart for N MOSFETs. VGS is equal to VOV plus VT, or VOV equals VGS minus VT, same thing, just rinse and repeat, whichever, move this around. And this has to do with the fact that to turn transistor on, we have to crank up our gate voltage at least above threshold voltage, right? And then we call that voltage, which actually is effective, we call that overdrive voltage. Remember that? So this comes back and over and over and over. So VOV, I want to find, if I find VOV, I can easily see related to the gate to source voltage. And then it says saturation, which means I have to find the gate voltage and my drain to source voltage has to be bigger than that. Am I going too fast? So in same table 5.1, the saturation condition is given right at the top, right on top right. That saturation means VDS has to be greater than or equal to VOV. So we need to find VOV so we can find what is the value for VDS. Right? That's the question. Find the required VGS and the minimum required VDS. I find VOV, I can find both of those. Let's do that. So, okay, I'm gonna just plug in the values. Half times 2 times VOV is unknown, drain current is given 0.05. Here, I'm using it amps or milliamps, sorry. So this guy is milliamps, so I'm using this also in milliamps. For micro to I'm changing into milliamps. So this is the thing, that the kind of things you have to make sure when you are calculating. So my VOV squared will give me some value and I can take the square root and what I get is 0.22 volt. Right? Now, VGS is equal to VOV plus threshold voltage. So threshold is 0.4. It's given here. So my VGS is 0.62 volt. So I used relationship for saturation. So I found my gate to source voltage. So what is the condition on VDS now? It has to be equal or greater than VGS. As simple as that. It has to be greater than this guy. It has to be greater or equal to VOV. It has to be greater than, sorry, not VGS. So the condition for saturation is, can somebody tell me what's the condition in table 5.1 on the top right corner? Alfredo, you got the book?
Book at home.
You have book at home?
Yes, I'm at the school right now.
Okay. You are in the electronics class, man. You are without book. All right. Who has the book? Nestor, you got the book? You guys are adults, man. I don't know what to say if you don't have the book. All right, Nestor wrote the formula for what? That's for ID. I'm asking what's the condition for saturation in table 5.1 top right corner. Can somebody dictate me so I can write it down? Matthew, can you tell me what's the condition for saturation given in the top right corner of table 5.1 on page 263?
My book is still loading. It takes a long time to load.
All right, who has the book ready? I know Alyssa's got the book ready. She just told me the previous relation. All right, Nestor wrote it. Nestor, speak up, man, that you have wrote it. So it's VDS has to be greater than or equal to VOV, right? Now the question asks, what's the minimum required VDS? So I know my VOV, I know my VGS, which the question asks, I know my VOV. So VDS, minimum VDS value is what to get into saturation? It has to be minimum. It has to be 0.22 volt. It has to be at least this guy. Are you with me? Are you guys with me on this? All right. To be frank, if you have no idea what's going on, you guys need to come to office hours. All right. All right. So,
Professor,
yes, ma'am.
I'm sorry. So the previous formula I had already had written down, but I'm trying to find the table in the book. Can you repeat what page it's on?
Say it again.
The page number that the table is on with all this information?
263.
263. Okay. Thank you.
All right. So are we all here together on how do we find VDS minimum? Luis, I cannot see you, man. Bring the camera down. You do like this, but I have no idea if you're doing this to me or somebody else. All right. So that's the minimum requirement that needed to be met to find the saturation situation. Now, we have to repeat this for another IDS. As simple as that, in this relationship, the left-hand side, instead of 0.05, it's given to be, what, 0.2. So our relationship for drain current will become 0.2 equals half Kn prime is given times VOV is what we need to find, VOV squared. So VOV becomes 0.45. And the condition is that for saturation is that VDS has to be greater or equal to this guy. And here again, we can find VGS, which is the sum of overdrive voltage and threshold voltage N type. Right? All right. Questions? So we have talked about N-type MOSFET so far, and the N-type meant that so Mansoor should have got the attendance by now, so I should close my email. So N-type was simply stated the the base, or what you call the platform is p-type, and then the channel that's formed is made of electrons because we apply positive voltage, right? So we deal with PG, VGS positive so far. But we can also make a transistor in N-type material. And in this case, now we apply negative voltage. So we can gather holes here in this region, holes, all right, just H. So in this case, we call it P-type MOSFET. So in normal transistors now, we have in normal ICs, we have both kind of transistors. We use transistors of both P-type and N-type. And how we achieve this is a semiconductor material showed how we achieve this is we make a kind of a well of N-type material, and then we make P-type and all those things. On the same wafer, on the same chip, now we can create a small region of the opposite polarity or opposite, it's doping basically. And we can create, we used to have P-type transistors, but then now the modern technology has many more N-type, and they're all fabricated together. Hence, we call it complementary metal oxide semiconductor, or CMOS. You know, we hear CMOS, so this is what it means, that we have now opposite types of transistors, both of the same chip. It's difficult to fabricate, but what it gives us, we can do both kind of switchings. Here we are showing the both of two types, which are isolated between with a very thick silicon dioxide planted in between, which electrically isolates the two type of transistors. And they all are connected to the same body, but this guy has this N-type well to isolate it from this P-type doping. And we do this to get, so we have moved on to many more N-type semiconductors because the mobility for electrons is much higher. So which means electrons move much faster than holes. And there's a little bit more involved discussion to that. I'll not go into that, but just remember that electrons are smaller and holes are bigger. So which makes, I don't know how to say it, a truck requires much more energy to move to get to a velocity than a sports car maybe. So smaller vehicle moves faster, the bigger one takes, I shouldn't say fat people or thin people. I'll be picking on myself if I do that because I can't move fast. And so mobility, higher mobility for electron has resulted that now we do a lot more N-type, but P-type are still there. So this is just showing the cross-sectional area. So in this case now, to get holes together, we have to apply negative voltage. So you can see this negative terminal of this power supply is connected to the gate, which means we gather holes in there, and this source and drain are P-type, and they do start conduction when the channel is formed. So much of the equations and treatment is the same, and but the only difference is now we use negative signs. So because this is negative, so this has to be more negative, or sorry, so this is more negative, this is less negative to get to saturation, to achieve the same idea. But we will try to cut down on confusion on the negative signs, but we have to just like, for example, the threshold voltage, VTP is supposed to be negative, but we'll just use its positive variant like this. And VSG now, and VSD will be then positive. How do we draw this? So it's the same thing. So we are using the positive values just so we don't get confused. But the idea is that, yeah, the gate voltage has to be more than the threshold voltage again to create the channel and to start the operation. We'll use the similar concepts, but instead of Kn prime, we'll use Kp prime, and we'll use mobility of holes, like mu p, not mu n. Again, these values will be given. Oxide capacitors parameters will stay the same, but the other parameters, mobility, would change now. We'll use the values for holes instead of electrons, right? So you have to now understand what's going on. The current is flowing this way again. Now, this is again opposite to the flow of electrons. This is feeding electrons, this is ground, so electrons are going that way, the current is taken opposite to that. All right, so the relationships for P Mosfet is about the electron mobility is greater than hole mobility, so NMOS is more preferred. This is the way we write it. In circuits for P Mosfet, you will have to clearly see the difference between the signs for N MOSFET and P Mosfet, just looking at how it is drawn. And that would tell us what kind of relationships to use. So this for P Mosfet, the arrow is going this way, just to show the direction of current. And if you remember, for N-type, we were using to show the arrow going towards the source. And here we are showing coming out of source. That was N-type and this P-type. So similar characteristics, but now you have to see we are using the absolute values to compare, but it's still the same idea. The source to drain voltage has to be more than equal the overdrive voltage to move it into saturation region. And once it gets into saturation region, the equations slightly change. And then when we bring in the channel length modulation, then we add the factor lambda in there. It's table 5.2, which contains all the relationships for P Mosfets. And again, you need to know what is the situation in the question and what relationship to use. All right, so for triode, we have same way like before, this relationship, which this can be written as VOV with channel modulation. We change it and we write it like this. All right, questions. So current we take going from source to drain in this case. That's depicted in this relationship. Now for the P Mosfets, again, the idea of early voltage, which is the channel length modulation, comes in here as well. And that's something incorporated as drain current equals half Kp prime, the channel ratio, VSG minus VTP squared times 1 plus VST over early voltage, which you can also, early voltage is reciprocal of lambda. So you can write as lambda VST like it was shown on the previous slides. So a couple of things here. Now we are taking voltage between source and gate because of the, instead of writing VGS, we are writing VST because to show opposite polarity. That's just that, nothing more to it. And threshold voltage, instead of just writing VT, we are writing VTP. Again, the treatment would be the same like we have done for N MOSFETs. All right, questions. There's just a pictorial graphical way that you are in triode region. If you are smaller than VOV, you get bigger than that, we are in saturation region.